So we're really excited to have Gil Holder for our colloquium speaker today. Gil's a professor at the University of Illinois, Urbana-Champaign. After finishing his PhD at the University of Chicago, he was a postdoc here at the Institute, so we're really happy to have him back. After being a postdoc here, he was briefly at CETA before starting a position at McGill, which is where he was before UIUC. Gil is a theoretical astrophysicist and cosmologist who has worked on a very wide range of topics, from the very early universe and the cosmic microwave background all the way to solar system objects. And today he'll tell us about a similarly wide range of phenomena that can be seen in microwave. Thank you.
Right. Wow, so this is amazing. So I was on my way over here and I realized it was almost 25 years ago to the day that I came here as a grad student to give a talk about how great it would be to do sky surveys in the millimeter. And, you know, John McCall was sitting in the front and was doing John McCall things. And about halfway through my talk, this guy in the back who I never met before just yells, "John, will you shut up? I want to hear what he has to say." And it turned out it was Dave Wilkinson, and it was because they were just about to put in the proposal for ACT. And they had come over to steal my ideas. But anyway, so I didn't realize how amazing that was at the time, but all right. So I'm generally going to talk about a few different things. So I'm going to talk about millimeter wave surveys, just to give you a sense of what these things are. So almost everything I talk about is going to be in particular about the South Pole Telescope, because that's what I've been working on for several years. But for almost all the stuff that I'm talking about, you could regularly say ACT did a bunch of these things and the Simons Observatory will do a bunch of these things. It's just, you should think of this, I'm using the South Pole Telescope as a stand-in. And there's differences between the experiments. Some are better for some things and some are better for others. But don't think that I'm just, only saying that you should think about SPT. And then I'll break it into two groups of objects. So objects and splotchy things. So that's what you do in a millimeter. You either do objects or you do splotchy. That's what we're gonna do. So just to orient you, what do I mean by millimeter wave surveys? So what I mean are these telescopes. So here's what we got, like things like SPT or ACT or the Simons Observatory, or Bicep Keck, or so up there we have WMAP and Planck is in there. And I've plotted this as the sensitivity to CMB fluctuations, because that's what the people building CMB experiments care about. And so the unit of that is micro K arc minute. I mean, if you have a 1 arc minute beam, it's a 1 micro K RMS. So what do you see? You see that we're getting to the point where these experiments are measuring a few micro K RMS on this 2.7 K background. And then in the case of Bicep Keck, they're starting to actually get down below that. And then so these circles are just kind of saying roughly either where things are now or where things are looking to go. And then here's the beam size. So you see it kind of breaks into two chunks. So these are the people that are trying to go after R. So if you're looking to do large angular scales, go after the inflationary background of gravitational waves, you're going to be out here. You only need degree scales because that's where the signal is. And then the people here are doing high resolution CMB experiments. And then what you see here is this is constant point source flux, or these lines here. So this is 10 millijanskis up here. So you see, once you get way up there, it actually starts to be hard to measure individual sources. But if that's 10 millijanskis, this is 1 millijansky, this is 0.1 millijansky. And, some people would call that 100 microjanskis, and then that sounds really good, right? So once you're at 100 microjanskis, you're doing astronomy. Like that's the unit that people use in VLA surveys, or microjanskis. And so that's where these experiments are getting to. And so different things in here. So you see that's where we're headed. And then someday, so 2029, we'll start the new SPT survey where we're going to try to get down there. It's legitimately things we can call. All right, so these are the millimeter wave surveys, so that you can do CMB things, that's the splotchy stuff, or you can actually just look for individual sources. We'll talk today. All right, so here's the South Pole Telescope. So this is what a lot of what I talk about is going to be based on, is this thing right here. There's been many generations. So currently we're on the SPT 3G generation. So it's something like 16,000 detectors at 3 frequencies and with IQ and U. So we don't do circular, but IQ and U. And so in general, 3 frequencies, 90, 150, 220, and roughly 1 hertz. That's where we are. So it's obviously a big collaboration. So no one would ever let me near a telescope with a screwdriver. So there are lots of people in here that did all the building of the experiment and analyzing the data. All right, so here is a millimeter wave sky survey. This is the SPT 3G. So in fact, it turns out we have a bunch of sky surveys built in. So I guess if we actually planned for this, we would have said we had this tiered strategy. Instead, we just kind of did this hobnob thing where we looked wherever we could. So we have this main survey right here with 3G. This is 1500 square degrees. And at this 1500 square degrees, where we're trying to get to is something like a few micro K arc. So that's roughly the goal. So that's fairly deep. Now, this turns out the sun is there. And so every once in a while, the sun kind of gets close to here. And so we can't actually look at this field for 12 months of the year. So for some other months of the year, for a while, we did these summer fields. And that ended up being 2800 square degrees. But because it was less time over more area, the noise here is, something like 8.5, 9 microhertz. So it's noisier. And so this is kind of roughly around the noise levels of what ACT finished up at, somewhere around there. And then we had a year and we were kind of a little bit ahead of schedule. So we roughly just took a year off and just tiled everything that we could look at in the southern sky. When you add that up, it ended up being another 6,000 square degrees. With the noise, it's another factor of 2 or so higher. So we have all these different surveys going on.
Out of curiosity, how much of the noise is driven by having the sun above the horizon? That is.
We don't really see a difference between sun up and sundown. So it's not we don't notice. And obviously, if you look right at it, you notice. We try not to do that. So these are the different surveys. Now, this red thing right here, this is the bicep patch. And we'll come back to that later. And what you see is that that's, roughly centered in our main survey, and that's not a coincidence. So that's one of the goals of this experiment, is to make sure that we combine with those properly. All right. Skip over that one. So let's just get a sense of what we're looking at here. So there's the Planck map at 143 gigahertz. And then here's the SPT 3G map at 150 gigahertz. And so our map is a little bit filtered, but they're filtered roughly the same. And what do you see? Well, you can break this into a whole bunch of different things, but I think in general, what I see when I look at this is I see a bunch of bright spots and a couple of dark spots and some splotches. So that's what I'm going to talk about. I'm going to talk about the spots and the splotches. The splotches are the primary CMB. The bright spots are emissive galaxies of some kind. And then that thing right now, there is a massive galaxy cluster that you can just see by eye, which 25 years ago, no one had ever detected an SE cluster by just looking at a map. People had to build custom experiments to do this. So it seemed crazy at the time I was talking about that. Right, so what are these dots? Well, so here's what these dots are. So we'll get to that in a bit. And then what's the splotchiness? The splotchiness is the C. Well, that's my talk, and then I'll do it in more detail. Okay, so what are the dots? So here's a almost raw 95 gigahertz map, and you see the color has been stretched. There's these large scale splotchiness, the map's been filtered, but there's still some dots in there. And so this was Melanie Shipley's PhD thesis. If you go through and you do a matched filter, so you say, let's get rid of all that splotchiness because we know what the CMB is pretty well, then here's a map. And so these are all galaxies. And so now you can see that while this thing seemed like it was a CMB experiment, it's actually a galaxy. So the 5 sigma limit's 1.3 millijanskis. So this is the 5 sigma limit for this particular map. Now, if I said it's a galaxy survey, let's convert this into magnitudes. And what you see is that magnitude limits as AB magnitudes, 16. So it's a galaxy survey, but not a great, right? So people these days talk about optical galaxy surveys where these things are measured in the mid-20s, things like that. So we're kind of, if you map this into other experiments, it's actually sort of similar to 2MASS. That's where we're looking at like a 2MASS level galaxy survey. But it's not bad, right? Because it's sort of the first generation of these surveys that's going on.
In that analogy, are you assuming an SCD and saying what you can detect in SPT is what you could
So
detect
for like an AGN or something. If you took an AGN SED, that's about what 2MASS would be. I mean, if you took an optical galaxy, obviously it's not very bright in millimeter. If you took a super dusty galaxy, it would go the other way. So this is roughly similar to 2MASS for sort of AGN. So what are these things? So here are the number counts. There's a lot going on here. So this is the number, the cumulative number per square degree. And here's the SPT limit. And what you see is we have something like almost 10 per square degree where we are. And that's, not quite what 2MASS has, just because we don't see galaxies like stars very well, although we do see some stars, it turns out. And they roughly break into two classes. So they break into dusty star-forming galaxies. So because we have 90, 150, 220, so we can get the spectrum. They're rather dusty. They tend to be either dusty or have some falling thing that looks like synchrotron. So our synchrotron counts, so these are blazars. Basically all of them have bright radio counterparts. So we have a bunch of blazars. And then there's this population right here. So this blue thing right here are strongly lensed high redshift dusty star forming galaxies. And so why do we see so many strongly lensed things? Well, so here's the unlensed counts. This is if you just do a theory prediction for what the unlensed SMGs are, normalized, what you should see. So it turns out you take some fraction of these, you take the 10 to the minus 4 or whatever of the sky that's lensed, and then you lens them, and it takes all these things and it moves them up here. And this, if you try to do this in the optical, it doesn't work very well because it turns out that you see a bunch of really bright things that just happen to be nearby. However, these dusty star-forming galaxies turn out to kind of run out of gas around redshift of maybe 1.5. There just aren't that many of them. And so it means you don't have that background of intrinsically faint nearby things that would swamp you in optical surveys and things like that. And so if you just take everything you see that's bright, it turns out it's going to have a high probability of being strong enough. And so there is a small number of nearby star-forming galaxies. You hack them out, and then you take this sample, and something like 90% of them are strong lenses. And so you see we have almost one strong lens per degree that you just pick out of the map by saying it's dusty and at high redshift. So there's one example of it. This is a famous one, SPTO 418. This is a redshift 4.2. And you look at that and you say that looks like an Einstein ring, right? So that's the ALMA image of it. Our image of it is a dot. And then we have the blazars down there. So that's some of the stuff you can do. But this one was actually one of the first targets for JWST. So once JWST hammered on it, you started actually seeing the host galaxy as well. So there it is with SPT, right? In all its glory. That's it. And then you follow it up with ALMA and you go, holy crap, that's pretty neat. DES, you see nothing. Like literally nothing is there in DES. Well, not literally nothing, but it's too faint to see. HST, you can start to see the host. And JWST, you see both the host and you actually can start to see the source itself. So some people have made some hay with that as well. All right. So there's also the dots. So what can you do with the dots? We haven't quite figured out what to do with the dots. So one thing you can do, like the non-dusty ones, the AGN. So what do you do with the AGN? So one thing you can do is you can watch them. So we survey this guy over and over again. So you can watch them and they jitter around and do crazy things. So Alan spent some time thinking about what to do with the variation. Alan Foster's up here, works now on SO. So this is just the flux as a function of time. You see it jitters around at factors of many level. And whenever someone joins our collaboration, they see these AGN and they see these big jumps and they say, wow, that's varying a lot for an AGN. Is what everyone first says. And then after about 6 months, it's just normal. So it's like normalization of deviance that you look at and you say, this is crazy how much these things move around, but then after a while, you just accept it and move on.
Do you have any idea what the lens was for that Einstein ring? Is it unusual to get such a perfectly symmetric ring out of, let's say, a galaxy?
Well, it's not a super odd lens. I mean, part of it is that we have, over 100 of these things. And when it's perfect like this, it is also highly magnified. So there's a selection effect going in that, the closer you are to the Einstein ring, the more magnified it's going to be. So there's some stuff
It's
going
not an
on.
elliptical potential.
I mean, you can see it right there. There's the HST image of the lens. It's just kind of an elliptical potential. I mean, it's not a perfect ring, but it's pretty close. But it's not odd. It's a fairly mundane lens. So actually, I have a student who's trying to model this to see if we can detect some small substructure from lumps in the lens. So we'll see how it goes. We haven't found any yet. All right, and then there are the dark dots. So what are the dark dots? Well, the dark dots are the Sunyaev-Zel'dovich effect. So you have the CMB photons come in, they get upscattered. When they get upscattered, the low energy CMB photons get bumped up to high energy, which means you have a deficit of low energy photons. And so because of that deficit of low energy photons, you see it as a hole in the map. And so these are these SZ selected galaxy clusters. And so if you then follow them all up and get redshifts for as many as you can, and that's actually a tricky thing. You see these things out here. It turns out you can't actually get redshifts for all of them. All you can say for some of them is that there seems to be something there, but we have no idea where it is. And so this is the mass versus redshift here. And you just see that we're now in this regime where we have large catalogs of sort of 10 to the 14 above galaxy clusters that have been selected using different experiments. So the Planck ones are down here, and then ACT is sprinkled through there selectively in behind all our points, so you can't tell how many they have. And then the SPT ones are on top, and this is the most recent catalog. So we have lots of galaxy clusters, and it's a fairly clean selection because it's just selecting on the thermal energy of the gas. So that's what I talked about 25 years ago. And you could in principle do cosmology, which I thought was a good idea at the time. Now I'm not good. But this is a safe space to say that. That's okay. All right. So as I said, the sun's up sometimes. So one of the things we did when we couldn't think of what else to do was look at the galactic center. So we have like 3 years of staring at the galactic center. And it turns out it looks kind of complicated. So there it is. There's a bunch of stuff there. So what this person was looking for at UG1 was actually, she was looking for transients. And so she did find a couple transients. And then what we also have is some monitoring of Sagittarius star by Paul Jachura, who works on EHT. And so we actually just have like, weeks of observation, a few different epochs of Sagittarius star. And so that's, if you can think of uses for that, and you're thinking about the variability of the Sagittarius star accretion and things like that, that's data that we have. So she found 2 transients, but I'm going to talk about transients in general right now. So the way we survey the sky is we have this 1500 square degrees, and we just basically roughly every day survey that 1500 patch. We have it split into 4 patches. But it means we have just daily measurements. And so for, I don't know how many years, we took all this data and we would just add it to the COAD. And we never looked at it. Just added it to the COAD. And then one day, I think Nathan Whitehorn was the one that really pushed this. He said, you know what, why don't we actually just look at the data before we add it to the COAD and see what's there? Like, it's not crazy to do. But we thought, like, it's the CMB, it's not going to change. So this wasn't the first one we found, but here's a map from SPT, and you see some sources, and then hopefully, because we're at the IES, the projector's good, you can see all the splotchiness a little bit. That's the CMB. And then here was one particular day in 2020. This is the COAD. This is averaging over hundreds of observations. You see just some bright sources in CMB. In one particular observation, something is different. And then the next day, it's gone. So what I really like about this image, other than the fact that you can see that, is you can also see this persistent blue emission, which correlates with this, which is to say, in a single 2-hour observation, we're actually imaging the CMB. So that's where we are now in CMB experiments. That a single day of observation is enough to sort of see the hints of the CMB. Okay, so there's a dot. And so you look at this dot and you say, well, that dot's basically as bright as these other dots, and then it disappeared. So what is it? Well, it's a stellar flare. So you just look at the flux from that image and you plot it on top of like a WISE image or something like that. You see the diffraction cross. So this is some variable star. It's Z end. But look at how bright this thing is. This thing is 600 millijanskis.
What's
One
the,
day.
what's the mechanism to give you vision at those wavelengths?
Well, that's an excellent question. So that's what I've been trying to figure out. So I'll give you my guess for it in a couple seconds. So I have a guess. So anyway, so here you see our data. So this is the sort of roughly 5 millijansky RMS. And then maybe it flared and then had a flare and went back down and went up again and then just totally quiet. So that's what we got. So we now have a whole bunch of these. We get one roughly every 2 or 3 weeks. We get a stellar flare in our experiment. And then you look in Gaia and you say, what's there? And it turns out if you just compare it to like the background HR diagram or color magnitude diagram of the stars you see in Gaia that are within maybe a kiloparsec or something, you see that it kind of breaks into some different classes. We have a bunch of things down here that are basically, they're kind of M dwarfs, but you see they're a little elevated. So we think they're mainly young M dwarfs. And then there's some things over here which are a little weird. And then we have a big clump right there. And this is just, especially down here at the bottom of the subgiants, they're all right on top of each other. We have a whole bunch down here. And so we think that these are basically evolved stars with some companion that are undergoing some interaction. So you look at them in tests and you see them, you have short rotation periods and things like that. So what are they, as Michael asked? Well, so for one, if you convert this into nu L nu at 150 gigahertz, that's this axis. And you see that we're getting like up to 10 to the 31, almost, 10 to the 30 ergs per second, which I guess in some sense is not very much energy for people that do, high energy astrophysics and things like that. But these are stars, right? Like these are M dwarfs, which are fainter than the sun, that are getting, a fraction, solar luminosity is kind of up there, but it's all coming out in the millimeter. So what's going on? So most of them tend to be quiescent X-ray emitters. We have never caught one going off in the X-ray at the same time as in the millimeter.
So I got to interrupt with yet another question.
Yeah.
Do you have parallaxes for all these?
Yeah.
They're all bright enough to be in Gaia?
They are all easily bright enough to be in Gaia. I think the faintest one we found is, I think, magnitude about 14.
Oh, these are
Apparent
really. Oh, so
these are all like within a kiloparsec,
okay.
and they're pretty bright. So we're yet to have one that we couldn't find a plausible association for.
That's almost surprising in a sense that there's a distance limit to them. But
Well, so part of it is that our main survey is looking out of the galaxy.
Huh? Yeah.
Right, and so
Yeah.
you're looking out of the galaxy, so we kind of run out of stars once we get to a kiloparsec along that line of sight.
Got it. Yeah.
There might be an edge to the M dwarfs, we can talk about that later. Because we think that a bunch of them are actually from this young stellar association, that they might all be of the same age, and so then we just see the edge of that association.
Are they detected in all 3 of your bands?
Yes. So they're detected in all 3 bands, which means we can get spectral indices. And so you look at the spectral indices and they're all over the place. So this is, S goes as nu to the alpha. So here's the index between 95 and 150. There's from 150 to 220. So something that's consistently rising is up in this top quadrant. Something that's consistently falling is down here. And then this is one that would be going up and then down. This one would be going up and then down. And this one here would be something that goes down and up. So you see they're sort of all over the place. There's some that are down here. It's especially the case that for these ones, we actually have not measured a 220 very well. So there's a huge error bar on these. But you see that for the most part, they're clumping up here. Which is to say they're clumping at the level of they're gently rising, flat to gently rising, something like that. So this is another puzzle of what's going on. So what's going on? So So what I think is going on, so here's something that explains everything, right? The philandering string theorist or whatever it is, I can explain everything. Anyway, what's going on? So something which explains everything is that it's just optically fixed synchrotron. Moderately optically fixed. So it's only gently rising. Maybe it's starting to turn over. We're kind of there. But if you just kind of do some basic like back of the envelope thing and you say if there's some kind of equipartition between the relativistic electrons that give you the synchrotron and the energy and magnetic fields, and you assume that it's optically thick the way you see. So this is this old argument, this minimum energy argument that goes back, more than 50 years. But if you just say, we assume it's optically fixed synchrotron, and you can then take the measured flux and turn it into an estimate of either the magnetic field or the size or the energy. This is really just a way to reparameterize the observed flux and then assuming that it's optically fixed synchrotron. If we know the distance. So you can turn it into some estimate of either the magnetic, so the magnetic fields that come out of this are somewhere around, 50 to 100 Gauss, which is not bad for a star. Seems roughly what a star should be for these things, like, the young M dwarfs or interacting binaries. The sizes come out to be some fraction of 10 to the 10 centimeters, which are kind of characteristic stellar sizes. Because, and what we see are now we're starting to see two humps. These two humps actually map into the M dwarfs and these subgiants. And so the M dwarfs are sort of smaller than the sun, and the subgiants are a little bit bigger than the sun. Seems plausible. And then the energies come out to be some fraction of 10 to the, there's 10 to the 35 ergs right there. There's, factor of 100 smaller. So it's a fair bit of energy to be coming out.
So if that's what this is, isn't there also the X-ray or something emission of those electrons hitting the optical photons from the photosphere?
There should be X-ray emission. Unfortunately, we don't have any coincident imaging because the problem is we see these things, it goes off in a 2-hour observation at the South Pole. We find out about them about 12 hours later. So there is quiescent X-ray emission. So there's definitely some of that going on. So what I think is happening is that there's just some big dump of energy. And you have this ball of synchrotron emission, and that's what we're seeing. And that it's on for maybe less, an hour or something. And then that energy seems to be roughly gone.
But what energy would the inverse Compton be coming out?
I don't know. I haven't done that calculation. But we have looked in the optical, so we have a few of these where Tess was looking at it while it went off. So we actually have some optical observations where we can see the flare happen in the optical, and in all cases, there is something there in the optical, but properties are all over the place. So trying to map the optical into this, I think X-ray would be better. So if we could get some coincident X-ray imaging or even UV. So I don't know if anyone here is like ultrasat or something.
Is any of them repeated? Any repeaters?
Yeah, so the repeaters so we haven't seen any M dwarfs repeat yet, but some of those subgiants have repeated. One of them's repeated, I think now 8 or 9 times. So one of them's just going often. And so this is the mystery of what we're trying to figure out what these things are.
Is it possible to do real-time on-site alerts? If you just do the image differencing, especially on the one that's repeated.
Yeah, so we do real time at the level of it takes us a few hours to do the processing. Our pipeline takes a couple hours to get through the whole difference imaging. So it is difference imaging on site. And then, so it takes something like a couple hours to get through everything there. And then often the satellite's not up, so we can't actually get everything sent up from the South Pole. So presumably someone like SO could probably do this pretty efficiently. And I guess that's what Alan Foster's job is to make this efficient for SO. Yeah.
I guess it is real time itself.
Do you have constraints on, you said it happens within a 2-hour window. Is there a way to get more precise than that?
Yeah, so we actually scan back and forth. We go to, roughly degree per second over, 100 square degrees. And so we actually can go scan by scan as we go. So the way we scan, we sort of go back and forth and then up a little and back and forth, and then our focal plane's about a degree across. And so something's in the field of view for about 30 minutes. And then we see it every, maybe 2 minutes or something, we'll get a data point where we can put it down there. And so we can actually do scan by scan. And for the most part, they're roughly unresolved. So we just see for the 2-hour scan. There's a couple where we see it go up and then come down. But for the ones that we just see that it's been on for that particular set of scans, we just have, okay, well, we know it was at least 30 minutes long. And then we came back the next day and it was gone. So most of them I'd say are probably longer than 30 minutes and shorter than a day. Is roughly what we can say. There are a few, there's one that I think the shortest we have is about 10 minutes. So went up and then came down in about 10 minutes. And so, yeah, the mystery continues. So part of the problem is we're hamstrung by the fact that we don't have very many people that know what's going on. It sounds like we have some people here that can help.
Are they polarized?
Not at the level we can see. We haven't seen any useful level of polarization. So we only have linear, so I think it'd be nice to have circular and see if something's going on, but yeah, we see no evidence of linear polarization, but then it's only the brightest ones where you'd expect we'd have a really good measurement, unless it's polarized at 20% or something like that. But we haven't seen anything super polarized. That being said, I wouldn't say we haven't really looked under the carpet all the way on that. So there's work to be done there.
What is the rate of your detections?
We get one about every 3 weeks.
Oh, if you're just wondering
Well-
if maybe your Rosetta might have them there, archival images.
We haven't seen.
I mean,
it's
you- of
difficult
course,
for the
some
Rosetta
across
for so
token.
short time to find such things. But I can tell you that we were very surprised. We have now 5 stellar clusters nearby. We analyzed everything. For example, Pleiades, which is just here, we see 860 objects, very bright in X-rays. They are thousands times brighter than our sun, and so on. It's very interesting because and enormous dependence on the age of the stellar cluster.
Oh, really?
Yes, in amount of these bright X-ray sources and so on.
Yeah.
It is there is a lot of data now from the Rosetta.
Okay.
We are publishing, I think 3 papers are in preparation, and one is published, 860 stars from Pleiades.
Yeah.
I think that this is 60 or 70% of all Gaia stars. Gaia associated stars with Pleiades. That we see from them X-rays, and they are very bright. And Gaia's is younger, and it has even more higher ratio of them stars which are bright in X-rays.
Yes. So I don't know if, yeah, I mean, we should be able to compare at least for a few. So I think Rosetta is seeing our patch, so we could compare even with these. But we do see all of these things we see in Rosetta. Basically all of it. I think maybe 1 or 2 of the M dwarfs we don't see in Rosetta as just steady sources, but it would be really interesting to see them flare. So the time domain in the Rosetta would be super interesting. But to go back to Roman's question, so it's only 1 every 3 weeks, but remember I said the way we scan the sky, we're only on a given patch for about maybe half an hour of every day. And so that means our efficiency ends up, when you do the calculation, we end up being efficient at the level of about 5%, as long as it's shorter than an observation. And so while we see 1 every 3 weeks, we're probably only seeing 5% of them.
That would be interesting, just, to cross correlate what your Rosetta has and you guys have, like contemporaneous, if there are any overlaps when the scan of your Rosetta goes through your patch.
But there's probably 1 of these going off almost every day in our patch, and just because of our scan strategy, we're missing.
Yeah, it's interesting to see
5% of them.
both of them at the same time.
Yeah, but even if you just had the statistics of how often something happens in Rosetta and how often it happens in SPT, you could probably do a statistical match.
Some of stellar flares have duration of the order of 40 seconds.
40
And
seconds.
we see them, and next time
Yeah,
spacecraft is going again, it is going at least
Yeah.
6 times we see the same star, 6 times per day. And nothing.
That's
Very bright.
So so right now we do our searching on the timescale of an individual observation. Where over that 30 minutes, we then say, did we see anything that went off in the difference image of 30 minutes? But there's an ongoing campaign to actually do it scan by scan. Every time we go across, did the sky change? And so that's development going on right now. And then we would have it localized to, sort of 2 minutes, less than 2 minutes.
How many stars do you see in general?
In general?
During your stars?
Depends on how you count, but a few dozen,
That's
a few dozen.
we have yes, we have on the half of the sky,
Yeah.
we observe a zone of 350,000 stars.
Yeah.
Which are confirmed, which are seen by God.
See, that sounds really good, but then our advantage is we only have a few stars, so they're easy to see.
I have too many.
All right, so anyway, that's it. So I'm around all week, so please someone tell me what's going on. So one last little dot. So here's a dot. So that's an asteroid. So it's not planet 9. So we've been looking for planet 9. We have not found any planets. So we could though, if there was a massive planet in the outer solar system in our patch, Alan would have found it in his PhD. So he didn't find it. And he's going to work on that paper. So another thing Alan did, this is probably so what is this? So this is an individual snap. This is our focal plane. And staring at the sky, and here's something going across our focal plane. Here's time in seconds. This is something going through our focal plane. So people that do optical astronomy know exactly what that is. It's a satellite. And what we're seeing here is the thermal emissions from this satellite. And so Alan and Aman did a dive in this just to see, is this actually going to be a problem? And it turns out it's not going to be a problem. But this is my favorite image of possibly the entire South Pole Telescope survey. So this is one that is in this paper. So what is this? There's a dot. That's basically not this satellite, but one satellite like this where you know the ephemeris and just track on it. And there's an image of this satellite, and this satellite is Kobe. So this is an image of Kobe as imaged by a CMB experiment. That's pretty cool. So anyway, it actually takes a lot of work to make this image, which is to say that in general, they're just kind of slightly annoying, but they're not. If you do the calculation, it seems like they're not actually a problem for CMB experiments, at least at the cell.
In a single observation, but maybe in a single scan.
In a single scan, but not in a coat. And the coat is going to be fine. They just go off all over the place, and so it's not going to be a problem. So I've always thought we should actually calibrate off of this, and then we'd have a Kobe calibration of SPT. People would be really confused by what that is. All right, so we got 10 minutes left for the splotches. All right, so what's the splotchiness? So the splotchiness is there in T. So at 220 gigahertz, 150, 95, it's also there in the polarization. So here you see the Q and U maps, and you see the characteristic boxiness. So Q map is all the fluctuations are aligned as boxes towards the north and east. And then in the U map, everything is tipped over by 45 degrees. And this is what an E mode is. So if you look at this and you say, these maps look funny to me, that's because they're E modes. They have no B modes in them. The B modes would all be tipped over. So the Q map in B modes would look like this one. And everything would be tipped over. So this is the E and the B modes. And so you just take these maps and you turn them into E and B. And then there's the temperature, and you can get the CMB power spectrum. So here's the CMB power spectrum of those splotches. So this was some heroic work by our French collaborators and with a few North Americans sprinkled in. So there's the temperature power spectrum. And so what do you see is we see a lot of peaks. And a single line for lambda CDM goes through those peaks really well. You also see that all the experiments basically agree. So there's in T, here it is in polarization. So there's Planck, and then the ground-based stuff kicks in. You see it goes in, and then out here is where the Planck beam starts to go on. It's just, Planck is actually pretty noisy in polarization. That's why these ground-based experiments are a good idea. It's because Planck's polarization is pretty noisy. And so you just trace these peaks, and then you can, guess how many peaks do you see that peak or not? And then it starts to run out of gas once you get out there. And then in TE, you see this characteristic cross. And so you just see there's one lambda CDM line that explains these points extremely well. So the main takeaway from this should be that CMB experiments right now are in very strong agreement with what they're seeing on the sky. And so if you turn this into constraints on lambda CDM, so let's just look at this panel right here. So this is H naught. So how well can we measure H naught? So here are the various combinations. So what are these combinations? There's Planck on its own. So this is the famous Hubble tension, is the fact that it's here and not over here. So just with SPT3G, we're a little bit broader. But you see we're still down here. We're definitely not over here. So there's SPT plus ACT. So what is SPT plus ACT? This is an entirely ground-based measurement of the Hubble constant. There's no Planck data in here at all, except a little bit on the optical depth. We have a prior on the optical depth. But this is just ground-based. And you see that just ground-based precision is actually pretty much the same as Planck. So now at the level of these ground-based CMB experiments are measuring the CMB in terms of cosmological parameters at roughly the same accuracy that you can do Planck. And so, of course, there's more ground-based stuff getting measured. There's no more Planck getting measured. So going forward, CMB means SPT and ACT and SO is what ground-based what CMB is going to mean going forward. And then you can combine them all. You can combine low L Planck with SPT and ACT, and you get this super precise measurement of parameters that's still again nowhere near there. But in general, I think the takeaway you should get from this is that the ground-based CMB is in excellent agreement with Planck. Everything holds together, and it's currently at similar precision, except for this measurement of the optical depth, which you can't do from.
If you've set the UMAP priority now, where does H naught go? I don't remember the genesis direction.
Oh, it barely moves. So we could take that out afterwards. All right, now, that being said, if you combine with DESI, things don't really work. So this is a long-standing problem, and we don't have anything new to say about this. So here's in the omega matter sum over neutrino masses. So the SPT points are all through here. So this is what SPT thinks the combination of omega matter and neutrino masses are. And so here's the normal hierarchy, there's the inverted hierarchy, and there's the best fit SPT actually is right on there. And everything looks fine. And if I didn't have this gray band in here, you would say, okay, well, we have some limits here. There's this correlation that's not too bad. And the problem is if you combine with DESI, the DR2, it comes down at this lower value of omega matter, and it just really clips the bottom of this. And if you combine them, you end up with these sort of alarming neutrino masses, where in principle, these massive neutrinos are not gravitating, they're not free streaming the way we think they are.
You remind us what is the lower bound on that sign?
This line right here. So this is the lower bound. So we know it's around 0.06 for the normal hierarchy, and then the inverted hierarchy, it goes up above 0.1. And so normally you'd say, oh, great, we actually have a cosmological confirmation of the normal hierarchy, except now we're starting to rule out the normal hierarchy. And if you include all the other data, it starts to become like, it really puts a lot of pressure on even just the normal hierarchy at the level of people are starting to rethink what's going on. But it mainly comes, so the CMB on its own, everything sort of holds together. It's just when you start folding in DESI, things don't fit very well. But again, this is just lambda CDM. If you open it up to some weird dark energy, this tension goes away. So when you say there's hints of cracks in the standard model of cosmology, it's coming from largely when you're combining these different things. So the CMB on its own, everything is fine. It's just you combine it with DESI and you start seeing sort of some weird thing. But this is not new. This is just saying we see the same weirdness that everyone else sees. All right. So let's skip the Bayesian stuff. So this actually has the plot in it that you want, but we'll come back. So we'll see that one later. So we also have lensing of the CMB going on, right? These photons come from less scattering, they get distorted. Go back to here. So here is the most likely CMB lensing map. So this is a full Bayesian analysis where you basically just sample over all possible foreground lensing fields and all possible CMB backgrounds. And so you have unlensed B modes getting lensed by this thing right here, and it's likely going to give you B mode maps that look like this. So this is Marius Malaya really pioneered this stuff. Faye did a lot of this, the actual heavy lifting on this. So it's a large sampling problem over here where these are all parameters that you're marginalizing over, and this is just the best fit. So that's what we think the CMB has been lensed by. And this is using just the polarization because we haven't quite figured out how to Bayesian model the temperature. So we have these CMB lensing maps. And so actually, I think Frank was a student here when he did this. Is this true? Anyway, so he had the bright idea of saying, well, you have these lensing power spectra. So here were the CMB SPT3G lensing power spectra. So that's just taking the power spectra of those maps. There's the ACT DR6 ones. And he said, well, why don't we actually combine them along with Planck? And we have this combined constraint on CMB lensing, where we're now starting to get another power spectrum with little itty bitty error bars on it, which we can use for cosmology. So here's another view of the SPT lensing map. So this is basically an optimally combined Planck and SPT lensing map over some patch of the southern sky. So I think what you can see here is that there's a patch where it's measured at much higher signal noise, right? Mm-hmm. So this is the SPT patch. And you just see that we have a lot more power on small scales. And it's just because, we have these much deeper maps in this one little patch than Planck does. And so this, the analysis of the power spectrum of this is actually, the paper is about to get into working review. So it should be out some number of weeks from now. However, so something that my student's working on is taking this map right here and cross-correlating it with shear maps. And so why would, what's the gain here? So here's the slide that he just, this is from Aaron. So Aaron's done some heroic work here, but so just to compare the noise levels of these maps. So this map is the SPT map. There's the Planck map. So you want to put this in power spectrum language. Here's the noise power spectrum of that Planck map. And here's the noise power spectrum of that other one. So you can see that we have something like, roughly a bit more than 10 times lower noise power in this part here as out here. And the other thing that lets us do is it lets us go out to much higher L where we're actually imaging the modes, right? So the Planck is only doing several degrees. And out here, we're signal dominated out to much smaller scales. And so this is just talking about the noise in this map. That's just the pixel noise. Now, if I was to zoom out and show the whole sky, what you would see is that Planck actually has the entire sky that looks like this, whereas we just have zeros. We only have this patch. And so similarly, ACT DR6, so that's the last release from ACT, has lower noise than Planck. Higher noise than us, but they have much more sky area. So if you start saying how well do you measure power spectra, these things actually are very complementary. And that's why it made sense to do this combination, is because out here, SPT has lower noise, and in here, ACT has better sample variance, and in here, Planck has better sample variance.
So theory there is standard lambda CDM.
This is standard lambda CDM, yeah. This is the Planck best fit, I think. All right, so we have these deep maps. Now, the other thing is that with 3G, with SPT, you see we have three lines drawn here. We have, if we only use the temperature data, if we only use the polarization data, and if we use all the data. And why is this interesting? Well, because the sky, the extragalactic sky is full of galaxies. And those galaxies are emissive, right? Those are all those dots. And so there's all the dots we see, there's also all the dots we don't see. And those dots tend to be clustered, so people have made careers out of this, right? People here have made careers out of the clustering of galaxies. And people have looked for the non-Gaussianity of the clustering from, gravitational instability and things like that. So the extragalactic sources are non-Gaussian and showing up in temperature. Now, what's nice is that they're almost completely unpolarized. So the HEN are polarized. But those are mainly just unclustered. You just have a bunch of blazars that are random polarization angles. But the cosmic infrared background, as far as anyone can tell, is completely unpolarized. And the Sneijder-Zeldovich effect, it should be roughly unpolarized. It'd be really nice to detect it, actually. I think people spend a lot of time trying to figure out how to detect the polarization of the SD signal. But the result of that is that if you're measuring CMB lensing, it is sensitive to these extragalactic foregrounds, the CIB and SE. Whereas because those are unpolarized, this polarization signal should be a cleaner channel. So it should be, we think, largely immune to extragalactic foregrounds. And so you see that you kind of lose some signal noise out here, but you don't lose much signal noise by only using polarization on lower scales. So what Aaron did is he basically said, let's just cross-correlate the large scales with the DES shear map and do polarization only. So he did DES shear maps. So he used the public shear catalogs and also the blue subsample, which some people here have had a big part of. And just doing a cross-correlation just to make sure everything makes sense. And so there's the DES galaxies, there's the SVT patch. You see there's this region in here where we can do this cross-correlation. And so there it is. So we have a detection of a cross-correlation between the SPT3G polarization-only lensing crossed with DES-Y3. And this comes out to be something like 12 or 13 sigma. And so this is comparable to the existing best detection of this using all CMB lensing combined. So now we're deep enough with polarization only that we have some version of this that we think should be largely immune to foreground.
These are redshift bins.
These are the different redshift things, yes. So you see a low Z and you see almost nothing just because it's not a very good lens. All right, I have one last thing I want to talk about. So B modes. So I talked about the E modes. So here are the B modes. So Jessica, who's about to start a faculty job at Chicago, did this heroic deep dive into the SPT data and managed to extract B modes. So here, this is the lensing B mode signal right here. And after this heroic deep dive, we have these red points. And this is the first detection of these large angle B modes, down at L of 100 using a ground-based CMB experiment. So it really is incredible work. And so this gives a sigma R of about 0.067, which not bad, but you look at this plot and you see these other points. And those are the bicep Keck points. And so this was kind of a proof of principle, like, can you actually do this from the ground? And the answer is yes, you can do it from the ground with a large aperture telescope instead of remember there was that first plot where the SPT stuff was on the left and then bicep Keck was on the right. No one had really measured R down here with things with high angular resolution. So it's possible, but still it's not as good as it could be. So we come back to this. So there's the bicep Keck patch. There's our patch. So currently the limit on far and away the best limit on R is coming from people studying this thing right here. But what they're currently limited by is the generation of lensing B modes. So the fact that you lens the E modes into B modes is the limit on R. And so we've joined forces, this thing called the South Pole Observatory. So it's SPT plus bicep Keck so I wouldn't say it's a full merger. We're trying to figure out the politics of how to get along. But we have combined efforts on the search for R, which is to say the goal is for SPT to remove the lensing effects from the bicep data. And the reason you want to do this, so here's how well you can measure R. And here are the bicep points. And then here's roughly where they are now. So if you don't remove the lensing B modes, so if Bicep Keck just kept building their experiment, and then, they're making their experiment better, so you see little changes in the trends, but they would saturate out here around R.005 or something like that. If instead you combine with SPT, and if we actually remove the lensing effect from their maps, then that reduces the sample variance in their measurements. And so that allows them to be better. So depending on what you assume about what the foregrounds are doing, and now it's the galactic foregrounds, not the extragalactic ones. You see that once you start delensing, this is SPT removing the effects of the foreground. So this is, when SPT 3G turned on. So if all along we had been combining forces, as SPT got deeper and deeper and deeper, we'd be cleaning out their maps for them. And the combined effect would be a factor of 2 or so better. And now this is bicep array turning on, and now it's getting better. And then here is the new thing, SPT 3G plus, where we're going to swap in that new camera. The new camera is going to be something like 7 to 10 times faster mapping speed. So we're going to be much more efficient at mapping out those lensing B modes. And so without combining forces, they'd be saturated out here. You combine with the current SPT camera, and then in a few years we'll be down there. We upgrade the SPT camera, and you see that we're getting down below this target of 10 to the minus 3. And this is 2034. So these lines right here, for 3G plus, that's just assuming that the experiments just keep going the way they're going. So this is not, we don't have to calibrate anything. This is just saying the square root of time is going to be our friend, and we're not going to hit something we don't understand. And then this is the new camera. So it's supposed to be 2029.
Where would you put the limit imposed by not quite understanding galactic foregrounds?
Well, so this is the decorrelate. So this is if you assume that we effectively know nothing about how well the foregrounds are correlated as a function of frequency. So Bicep Keck now has a very large number of different frequency channels. And so this is where they think they are limited by the decorrelation of the foregrounds across frequencies. So that's this line right here. And so, so there's some uncertainty in exactly what happens there once you get down there as well. So we'll see. All right, so there it is. So I talked about spots and splotchy fields. Something I didn't say is there's a paper in progress, which is the data release paper. So the 2019-2020 data should be coming out as quickly as we can get a paper out. So I think at some point we agreed it'd be no earlier than November 1st that we could finish off analyses, but it looks like we're not going to make that deadline, but it should be relatively soon. And then for anyone here who's looking for a job, UIUC astronomy has a faculty open. Hopefully, I'm in physics, but I really like those guys. They're great. All right, that's it.
Did you say anything about extragalactic transients? And one in particular is you see a lot of blazars, there must be a bunch that flare that would go from below your sensitivity to suddenly undetectable to nothing. Do you see that?
We see a bunch of those. Yeah, we have a whole page of them. And again, it's this normalization of deviance. We see them all the time, and we see them so often that we've decided that we don't even pay attention to them. But they are flaring by factors. Some of them are flaring by factors of more than 10. They'll go from being undetectable at the level of a millijansky to going up to 30, 40 millijanskys, and then disappearing again a few months, maybe a month later, something like that. Some of them turn on and stay on, some of them are on and then kind of just fade. So there's all sorts of weird stuff going on with the flaring AGM.
Anything not in the flaring AGM category?
So we were hoping, so Nathan Whitehorn really got excited by this because he read some papers by some irresponsible theorists. It said that there should be these high redshift GRBs that would be highly extincted, that if there was this population of sort of POP3 GRBs, that it should be something that you would probably only see in the millimeter. And so we've seen none of those. So we're at the level where we should be seeing So just from the regular GRB afterglows, we think that we're at the level where we should have seen roughly one by now, just from what's already known about millimeter wave emission from GRBs. So we should have seen roughly one. We've seen exactly zero. So it's not intention yet, but it means that there's not some population of dark GRBs. We haven't seen any orphan afterglows or anything like that. So the other thing we've been hoping to see were reverse shocks in these GRBs, because that is we're seeing in ALMA. So again, we've looked for some short duration stuff that's not a star, and we haven't seen anything convincing yet. So, you know, TDEs are something that if it's close enough, we will be able to see it. So I think whatever the first TDE was super bright in the millimeter, like at a level of it would have been, you know, something like 100 millijanskis. So there's lots of stuff we should see. So supernovae, we should be able to see some late time emission from supernova ejectas leading into. There's lots of stuff we should be able to see, but we're only really starting to get serious, you know, getting a team together where people can look for all the different flavors of things. But if people have ideas for weird things, we can have a look.
Okay, one last question. And
Maybe
then
another word thing, any changing look AGN?
Well, what do you mean by a changing look?
Well, change of type from 1 to 2, or apparently.
So,
I mean, you won't see the broad line, you won't see the lines, but if you have co-imaging.
so an issue that we have is that our beam is, you know, roughly an arc minute. And so we kind of have like an uncertainty that it's hard for us to get much better than maybe 10 arc seconds or something like that. And the problem with that is, you know, it turns out there's a lot of galaxies out there in the optical. So we don't see them, right? So for us, it's no problem because there hardly any of them are glowing in the millimeter. But in the optical, like you just look in DES or something and you're like, oh man. You see like 4 spots there. And you're like, well, I guess I'll take the blue one. I mean, and it usually is the blue one, right? But so we haven't been able to, but again, no one has really carefully gone through and took all these things that changed a lot in brightness in the millimeter and carefully in existing optical surveys to see what happened. You know, they probably wouldn't have spectroscopy on most of these before and after. But that's a project that someone should do. It sounds perfect for us though, right?
let's maybe ask questions after book lunch maybe and have this election.